So for my last lecture, I would like to close the circle and go back to a question that was asked during the first lecture, very natural question. So we have those representations from mapping class group of sigma G in projective general linear group, so C. And one of the things we learned is that the kernel of rho R contains the subgroup generated by half power of Dehn twist along all simple closed curve on sigma. And so the question was, we have this inclusion, and is it actually an equality? So someone asked this question during the first lecture, and that's the thing we will try to address today. So first, I would like to quote a result that says that might be reasonable to think that this is true. There is actually some kind of deep work of Dehn and Marché of 22, which more or less says that this is true for some specific examples of the quantum representation. So this is true. Well, not quite. It's up to a finite index. So meaning that this subgroup here might be a finite index subgroup of this. If, well, two conditions. First, we want the part R to be equal to 5. So we want to look at 10th root of unity for zeta R. And we also want a condition. So here I said, well, even though I didn't define it for non-closed surface, the quantum representation, you can define them for surfaces with boundary. So here they found that this is true if you have that Gn is one of the following: 0, 4, 0, 5, 1, 3, 2, 1. Okay, so they prove it. But the proof that they provide for this fact is very specific to those values, because for those values they recognize in those quantum representation geometric structure on certain moduli space of curve, or rather twisted moduli space of curve, and then using algebraic geometry they find out that this is true for those values. So we will want to try to address this question for general R. But we will have maybe more humble goal, like maybe not show this inequality, but try to get as close as possible. And so we have this theorem with my collaborator, Ramesh-Santarban. From 23, which says the following. So we take, first case is we take R at least 5 prime. Well, let's say I will call it P then. And G at least 3. Then I have that the kernel of rho P is contained in the subgroup generated by, so this subgroup I will write it as KR, subgroup generated by all half power of Dehn twist. So here I say that this is included in the subgroup generated by KP and the commutator subgroup of the Tor. Okay. So we have this, and yeah, I realized I wanted to make a definition before stating the theorem. Well, let's say this is the first part of the theorem 1, which I can state. So we have this result, which tells us that well, at least the kernel here cannot be much larger. Well, it can be much larger than KP, but well, at least it's included in this. And I want to state a second theorem, which is a bit finer. So here, the Detcherry group, we defined it as the kernel of the map from the mapping class group of sigma to SP to GZ, which we could also think of as the outer automorphism of the atomization of the pi1 of the surface. Here, pi is the pi1 of sigma g. Okay, so I will want to rename the Detcherry group. I will instead write it as, for me, it will be J1 of sigma g. And I want to think of it as the first term in a sequence of subgroup of the mapping class group. And the second one will be what I call J2 of sigma, and it will be the kernel of them from mapping class sigma to outer automorphisms of, well, instead of taking the quotient of pi by just the commutator subgroup, I take the next element of the central descending series. So this is a definition, and this J2 of sigma is known as Johnson subgroup, or sometimes the first Johnson subgroup. And then you see how you can generalize this in an infinite series. You just take more commutators there, and you will have a J3, J4, etc. And so for me, well, I think of the Detcherry as the element just before the Johnson subgroup, and so I include it in the sequence. So I don't try to disrespect Detcherry by doing this. I just show even more respect to Johnson. Okay, so now I can, with well, before I state the final version of this theorem, just a remark, which is, well, theorem by Johnson from the 80s, which will give you a more concrete way of thinking of this subgroup, which is that J2 of sigma is the subgroup of mod sigma g generating a separating twist. Okay, so if you remember on these lectures, we said that the Detcherry group is generated by separating twists and those bonding pair maps. And for the subgroup, we just have the separating twist. Okay, so now I have second final version of the theorem. I will now take still P a prime, but here I will need to take it a large, and I also take G at equal to 6. In that case, I can say that the kernel of rho P is included in subgroup generated by KP. So I know this is in the kernel, so I need to have this subgroup. But also I will take now the commutator subgroup of the Johnson. Okay, so, and then, well, one obvious, so maybe another fact that is relevant here is that it's well known that when you take the intersection of those Johnson subgroups, I said you can define them for any k, you would get just the trivial subgroup. So with this in mind, the first are just kind of the first step in trying to prove that the kernel is just Kp. And if you could do it at any step, you will be able to prove give a positive answer to the question. Okay. So what will be our tool to prove such statements? Well, it will be, we will use the integrality of the quantum representation. So this is a property of quantum representation mentioned during the first talk. Quantum representation rho p for p prime. So I say that for p prime, we have that rho p can actually be thought as a map from mapping class group of sigma g to the automorphism of well, the general linear group with coefficient in the cyclotomic ring. Replace q of zeta p by z of zeta p. And when I have this, so the quantum representation is usually very hard to compute on specific elements. So we will want to weaken the quantum representation to be able to compute it, or at least compute some, find that some elements have well, better control the properties of the images of quantum representation. So well, we have this ring, and we have that zeta p minus is irreducible in that ring, the ring of cyclotomic integers. And this guy I want to call H. It's another fact. And actually, you can show that when you quotient z of zeta p by H, what you get is isomorphic to the field with p element, with z over p. Okay, so this is an elementary number theory fact. And so here to study both kernels, we will study versions of the quantum representation where we mod out by a power of h. So when we have a representation in here, so this is a ring, and we can take the coefficients mod h to the k, and we define then such a representation from mod sigma g to p GLD of z of zeta p over h. Okay, so then, well, what we will really show here is that to have this inclusion, we will get this inclusion just by showing that this is the kernel of rho p1, and this guy is the kernel of rho p2. So if we show that this is the kernel of rho p1, then the inclusion is, because when, yes? HK, yeah, I forgot the K here. Okay, so I will try to show this, and as a first step, I want to tell you more about the integrality of quantum representation. So we have a theorem by Gilmer and Masbaum that tell us that you have such an integrality result that you can find a basis in which the quantum representation takes value in this cyclotomic ring. And to be able to do computations later, we will need to know what bases those are. So I will try to explain how do you show such an integrality very briefly, and what are the bases that you get. So remember that we defined the vector space rho p of sigma by taking the Q span of the pairs ML with the boundary of M is identified to sigma and modulo the kernel of the bilinear form, which was obtained by when you close manifold with boundary sigma with another one with boundary sigma, and then you take the invariant. And so here there'll be Z of zeta p module, which I will call SP of sigma, which is the same thing here, but instead of taking Q of zeta p span, I take Z of zeta p span. And here, just formally, you see that this thing is a subspace, well, it's a sub Z of zeta p module of this, and that it's invariant by the mapping class group. So you at least, well, you get a Z of zeta p module that is stable, and also you see that when you tensor with Q of zeta p, you get back the full thing. So there's nothing hard here. But the theorem of Gilmer and Masbaum in 2007 is that this guy is actually a free Z of zeta p submodule. Module of the same rank as the dimension of this vector space. So this is just because of this. And they give an explicit basis, which is given by so-called lollipop trees. Okay, so what's the lollipop tree? So before, well, when taking, to get a basis of the vector space Rp of sigma, what we needed was to have a free variant graph, which was a spine of a handle body with boundary sigma. So here it will be kind of the same idea. We'll take a spine of the handle body, but not just any spine. So the spine here has to be so-called lollipop tree. So this is a lollipop tree. What does that mean? Well, you see that this thing is just a tree with trivial vertices on which I glued some one-edge loops on the leaves. I glued G one-edge loops if the surface is of genus G. Okay, and there is, so you want to use specific spines, but there is also something else that you want about the way you color the edges and how you interpret them as linear combination of links. So here you will color the internal edges, the ones that are belong to the tree. So if this is colored by you want to color them by even colors, and here we do as we did before. We cable and we put a Jones-Wenzel idempotent. But when we have a one-edge loop, now we want to color by color bi, which is now not necessarily even, but what we will want is that this thing is between 0 and r minus 3 over 2. And well, here next to a one-edge loop, we should have an even color because this is an internal edge. What are we doing here? We're replacing the internal edge by the 2i cabling with a Jones-Wessel idempotent. So here we can take AI strands and go around the loop. And what we do here is we add bi parallel copies of the loop. But here in this one, we don't put a Jones-Wessel idempotent. This is the only difference. It will make computations a bit harder because now the twist corresponding to this non-separating curve is no longer diagonal in the lollipop tree basis. So this is the thing that is a bit special. So here this twist is not diagonal. Does not act diagonally. So using this, you define vectors v, ai, bi. There is one last thing that you need to know, which is to renormalize by the right power of h. So the power of h will be of this form. I take minus 1/2 of a1 to ag. So here, those are the colors of the edges, the internal edges that are adjacent to a one-edge loop. So those are not all of the internal edges, just the one. Well, in this case, yes, but for a higher genus surface, it would not be all. So you will need to renormalize by this quantity, and then it gives you a basis of this submodule. So this is the thing. Yeah. Yeah. Yeah, okay. Yeah, right. Okay. Yeah, it's yes. Okay. So there is a corollary of that you get from this description of the basis, which is that the Johnson subgroup J2 of sigma is inside the kernel of rho P1. So why do you have that? So remember I said that, well, because our basis no longer has Jones-Wessel idempotent at edges for the loop edges, I don't have that the non-separating twist that the red curve here that I draw, it does not act diagonally in the basis. However, if I take this curve here, which is a separating curve, and I act on the basis with it, well, it will send this this trivalent graph to something like this, where here this is colored by F2AI. And well, we say that when we have a strand called by a Jones-Wessel and we twist, we get the same thing up to a coefficient. So we have that when we look at, let's say this is curve alpha. When we apply this to the vector AIBI, well, we get coefficient times V of AIBI, and the coefficient that we get is zeta p to the 2ai plus 1 square minus 1. Here, this is the color corresponding to the edge. And this guy is 1 mod h. Because h is zeta p minus 1, so zeta p is 1 mod h. So here, all the eigenvalues of the twist corresponding to this are equal to 1. So this twist is sent to the identity. But now, if I take any separating closed curve, I can complete it into a lollipop tree pair of pants decomposition of the surface. I can choose over curves so that this curve is and choose a spine of a handle body and blah blah blah, so that I'm exactly in this position. So for any separating twist, I will send it to the identity, and therefore, because the Johnson subgroup is generated by separating twists, it will be in the kernel of rho p1. Okay, so this is the first fact that tells us that the representation rho pk have to do with the sequence of Johnson subgroups. So now that we have that, we will start doing an analysis of the representation rho p1. And in fact, what we really want to do is to study rho p1 restricted to the Tory group. So we have a first fact that will help us, which is that when we look at the commutator subgroup of the Tory group, well, it's included in the Johnson subgroup, the J2 of sigma. So I won't try to prove this fact, but it's not too hard to deduce from the definition that I gave here of the Johnson subgroup. And well, so I will take this fact for granted. And you have a corollary of this fact, which is that the representation rho p1 restricted to J1 of sigma to PGLT of, I write FP because Z of zeta P mod H is FP. Well, this thing factors through the mod P abinization of the Tory group. So here it means I take the abinization and I also quotient by p power. Well, because we know that this thing isn't, we know that the commutator subgroup here is in the kernel of this map. So here it factors at least through the abinization. But moreover, we know that the Tory group is generated by bonding pair maps. So J1 of sigma is generated by bonding pair maps, which are of the form T alpha prime inverse, where those curves are disjoint. And well, I know that the power of the Dehn twist is killed by the quantum representation, so it's also killed mod H. And well, because the two curves in a bonding, yes, disjoint curves with the same, Well, yeah, I didn't mean to define what a BP map is, and we've seen it before, but we could, they have to be homologous for it to be a BP map. So when we take rho p of the BP map to the power p, well, they're disjoint, so they commute, and we get that this thing is trivial again. Okay, so
I guess one thing I didn't say, I thought that P is at least 3, you don't need to separate the tests.
Hmm. Yeah. For the separating twist, we can also directly show that the p power is strict. Yeah. Okay. Okay, so it factors through the mod p abinization, and well, you know from Andy's talks that we know a lot about the abinization of the Detcherry group. So in particular, we know about the mod p abinization, but Andy was talking about surfaces with one boundary component. So I will state what happens for surfaces with that are closed. So I will write H for the H1 of sigma with coefficient in Z. And I have omega, the intersection form. And maybe I want to write it as omega joule for a reason that will clear in a second. So with this intersection form, I can take any symplectic basis, A1, B1, AG, BG, and I defined an element of lambda 2 of H, which is A1 wedge B1 plus AG wedge BG. Which now, this is the one that I want to call omega. And this element does not depend on the symplectic basis that I chose for the homology. And so with this notation, I can give you the closed version of the theorem of Johnson that Andy mentioned. So this is again due to Johnson. We have that the abinization of J1 of sigma is the same as, so lambda 3 of H is what we were getting for the surface with boundary. Now we have to mod out by omega wedge H and plus a 2 torsion group, which is really finitely generated because one is finitely generated. So you get that the abinization mod P of J1, so I'm taking P at least 5, so it will kill the 2 torsion part, and I'm getting lambda 3 of H1 with coefficient ZP, mod that by omega wedge H1 coefficient ZP. Okay. So I have that. So here, as was the case in Andy's talks, a priori you have just a structure of an abelian group for the abinization of J1, but everything is endowed with an action of sp2g. So here this is sp2gz modules. And same below. Sorry? Yeah.
Extension, but you kill the kernel of the extension.
Yeah.
The kernel is the two.
Yes, if you want to
You mean here it's not as SPG2G module? Yeah, okay. Yeah. But here it's, so modulo the torsion, this is correct. This is an SP2GZ module. This is the SP2GZ module structure, and here too. Okay, so, well, that means that we would like to understand better this representation. So here, compared to the representation that appeared on this talk, this is a modular representation because it has coefficient in a finite field. So, well, one thing that we would like to know is whether it's irreducible. So I will write V to be this way. I say that V is irreducible if P does not divide G minus 1. And if P divides G minus 1, V is not irreducible, but it's indecomposable. But as a unique proper, well, non-trivial subrepresentation, which is the kernel of the following map. So map kappa bar, and kappa bar is the map from V to H, which sends an element A wedge B wedge C to omega of ABC plus omega of BCA plus omega of CAB. So, well, turns out that you have this structure for the representation. Well, it's not obvious, like you need to study the representation. And, well, the thing is that this map here is only well defined when P divides G minus 1, because here, a priori, the map that I define is a map on lambda 3 of H. But when you apply it to an element of the form omega wedge H, what you get is G minus 1 times H. So when P divides G minus 1, well, it vanishes on all of omega wedge H and thus gives a map on V. That is still trivial and thus has a kernel, and that turns out to be a subrepresentation. Okay, so so this is one property of the representation, and another one, which is easier to prove, is that V is a faithful representation of, so it would be a faithful representation of SP2GZ, but it's also a representation of SP2G of Z mod P. You can act by, like, you only need to know the coefficient mod P to know the action. And this is because SP2G of Z mod P is almost a perfect group for the parameters that I've chosen, which is G at least 3 and P at least 5 prime. As only its center, which is plus or minus the identity, as a proper non-trivial normal subgroup. So because this is a non-trivial representation, and because we can show that the kernel is also not this subgroup, it's faithful. Okay, so we have all the ingredients to show following proposition, which will, well, more or less, like, which is the key ingredient in the proof of the theorem 1, which is rho P1 restricted to J1 of sigma. So it's a map from, so from you can think of it as a map from the abelian mod P of J1 to J1. So I well, like this is a surjective map, and I say that this is an isomorphism. Okay, so this is the same as saying that the map rho P1 well, is injective, or viewed as a representation of the apization of P of J1. Okay, so this is the same as saying that the kernel of rho P1 restricted to J1 is the kernel of abinization. Okay, so what is the proof for this? Well, we have this map, and again, as before, this is a map SP2GZ representation. So the kernel here has to be a sub-representation of that. So in particular, if this is either an isomorphism or a trivial map. So in that case, we only need to show that it's not a trivial map. And to show that, well, you can try to make a computation on the simplest possible element that you can think of in the tori group, which is we want to show that rho P1 of bonding pair T alpha prime inverse is not the identity mod H. Okay, so this is a computation that you can do because you choose a bonding pair that and a lollipop tree basis that is adapted, and well, you carry out the computation and you see that it's not the identity model. Sorry. Yeah, sure. Well, actually, if this is non-zero, it means that there is a bonding pair which is non-zero because I part one. Okay. Yeah. But I checked this, and yeah. So now we have a slight problem when P divides G minus 1. So how do we take care of this problem? A priori, even if we know that bonding pair maps are sent to non-trivial elements, we don't sure that the kernel of the P1 restricted to J1 is the same as the kernel of the urbanization, mod P. So in that case, what we need to do is to find an element of the kernel of kappa bar, which is not sent to the trivial element. So in that case, well, we check that rho P1 of F is not identity mod H for F, what is the so-called simply intersecting pair map. So what is this thing? So I take a portion of my, my surface. Well, here it has just genus 2, but you can imagine that it has higher genus. And I take two non-separating simple closed curves, which I want to... What? Yeah, here, and yeah, that's why I'd like to have a genus-free thing. Yeah, that's right. So I want to take those two. So let's say A and B. And so those are two non-separating simple closed curves, which intersect algebraically 0 times, but geometrically 2 times. And I take F to be the commutator TA and TB. Okay? And so it turns out that this guy, we can find its image in the abinization of J1. Yeah. So so I can find out what is the image of this guy in the immunization of the Torley. This, well, you see that a regular neighborhood of the union of the two curves will be a four sphere, and so I have four curves that I draw in blue here. So this is X, Y, Z, and W. And I say that the image of this will be, so it's an element of lambda free of H modulo omega wedge H, and it's this guy. Okay, this is this guy. And, well, this thing will be in the kernel of kappa bar, because you see when you apply the formula for kappa bar, well, all three of those curves are disjoint. So when you try to compute the intersection, you get all those omegas over there are 0. So this thing is in the kernel of kappa bar, no matter which prime p you chose. And so a priori it suffices to do a computation for this guy to show that it's non-trivial to conclude the proof of it. So, well, it's a computation that you can do. Actually, we don't do this computation. What we do is we first know that the hybridization, the kernel of rho p1 will be an isomorph, rho p1, the map that I've written over there is an isomorphism for g equals to 3, because you don't have p divides g minus 1 for that case. G minus 1 is equal to 2, and p is prime at 5. And that means that in that case, well, when I look at the genus 3 surface, this guy will be the image of this guy by rho p1 will be non-zero. And then you argue that if it's non-zero and you add something to the surface, it will stay non-zero for the representation of the larger surface. Okay, so you have that, but if you wanted, you could try to do it with computation, and you would get the conclusion. Okay. So with this fact, the position now proven, we can finish the proof of theorem 1. So we take f in the kernel of rho p1. And here, contrary to what I was doing previously, f is not necessarily in the Torley group. It can be in the mapping class group. So what I say is that f acts on the image of rho p1 restricted to j1 of sigma by conjugation. Like when you have an element of j1 of sigma, conjugate by f, it will still be in j1 of sigma. And when you apply, so you will get an action of mod sigma on this space. Okay, but I know that this guy is the same as this is isomorphic to V. And I know that here SP2G Z mod P acts faithfully on V. So if my element here is in the kernel, here it should act on this guy trivially. But that means that it should be in the kernel of the map from the mapping class group to SPG of Z mod P. And, well, it's not, well, you can prove that this thing is same as Kp times 1. the kernel of this map is the same as this. Well, you need to know about congruent subgroups of the symplectic group to be able to prove this. So it's not a completely obvious fact, but it's well known. And well, because you have this and you know that Kp is in the kernel of rho p, so also in the kernel of rho p1, it suffices to consider the situation where f is in J1. So this means that without loss of generality, we can just show the proposition for f in J1. But then because we know that rho p1 respected to J1 of sigma has the same kernel of as the abinization of the Tory group, this implies that f is in the kernel of P, and the kernel of the abinization mod P is exactly what we want. So kernel of the abinization mod P, well, contains the it contains obviously this guy, and it also contains well, I should say K P intersected with G1 here. So it's of the form that we want, and we have concluded the proof of theorem. Okay, so in the last 10 minutes, I will just give you a few ideas how we generalize this to get theorem 2. And here we need obviously more machinery because we have to deal with it will have to deal with the next Johnson subgroup. So theorem 1, we proved by computing the kernel of rho p1 restricted to J1. So here we need to study the kernel rho p2 restricted to J2. That's the thing that you need to do here. So we knew that rho p1 was trivial on J2, but it's no longer when you, instead of looking at the representation mod H, you look at it mod H square, you get things that are no longer trivial. So that's what you need to do. And again, just as before, it turns out that it factors through the abinization mod P of the Johnson subgroup. Okay, so that means that we need to use what's known about the abinization of the Johnson subgroup. So we know that it's already something difficult to understand the abinization of the Tory group, and it's even more difficult to understand that of the Johnson subgroup. So we need two results for this. So we have a theorem by Morita, Sai, and Suzuki, which is from 2020, which describes what the abinization of the Johnson is as an SP2G representation. So the abinization of the Johnson will again be a SP2GZ representation, although the structure of representation is not canonical in that case. And we have the following. So in that case, so for J1, it was, we got just one irreducible representation over of SP2G of Q. And here we got three factors. So, yeah, rather I should say we look at the rational abinization. So here we get a trivial factor Q. So here SP2GZ acts trivially. And then we get two other factors. And the irreducible representations of SP2GQ, they are They can be described by Young diagrams, and so there are those two Young diagrams that. But more or less, what we care about is that there are three factors. Okay, but this is only the rational abelianization. So, and for us, we will want to look at the abelianization mod P. So we would like to know about not only the abelianization modulo torsion, but also about the torsion. Here, we will have to appeal to a theorem by Church, Ershoff, and everyone's favorite expert of the Tory group, which says I forgot to say here it's for G at least 6, and here it's again for well, it's true for G at least 6. I think maybe true also for 5. Okay. So 6 minus epsilon. We have that J2 of sigma is finitely generated. Okay, epsilon equals 1. Okay, so if this is finitely generated, this means that the torsion part of the abelianization is also finitely generated, and therefore, when I look at the abelianization mod P, for P big enough, I will kill all the torsion. And also you can, well, it's not clear that those guys will stay irreducible sub-representation, the irreducible factors of the representation mod P, but for P large enough, they will be. You will get that the abelianization mod P of J2 of sigma is, well, so you have an FP factor, which is a trivial representation, and then you have a modular representation corresponding to the same Young diagram, and also the third factor is also the same. So here, yeah, I should write it. It's for P large enough only. Yeah, we have no idea how big P. Yeah, and I think even for like what kind of torsion you get in the abelianization, here also you have no effective bound, I think.
We are now at least explicit there.
Hmm.
Super.
So now that we have this, the last part of of the strategy is to prove that each of those factors will not be killed by rho P2 restricted to J2. And well, I won't have time to explain much about this, but I will just tell you specific properties that each of the factors have and that are used to show that each survive. So we have that the trivial factor Fp, well, here those are not only, well, you can think of, there is a representation, not just a structure of a representation, not just of Sp2gz, but also you can make the mapping class group act on the abelianization mod P of J2. Because you can conjugate an element of J2, it stays in J2, and you can take the abelianization. So here I say that Fp is the only, well, actually, I didn't need to talk about the action of magic. So this is the only factor that not vanish on the fourth Johnson subgroup. And similarly, you have that the last factor is the only one that does not vanish on the commutator of J2 and J1. So here you have a map from J2 of sigma to this FP vector space, and I say that, well, and thus I can project on each component. So I have a map from J2 to FP, I have a map from J2 to box 2 square, map from J2 to box 3, 1 square. And I say that the only map of these three that does not vanish on J4 is the first factor. Yeah. Yeah. Okay, so you have those two facts. So here you see a strategy to show that each of those factors are not killed. Like you need to find an element which is not killed by rho P2, which is in J4. And you need to find an element which is in this subgroup, which is also not killed by rho P2. If you know that the first and third factor are not killed. So there is a last trick to show that the middle factor is also not killed, which is to look at the codimension of the image of this guy inside the image of J2 and show that it's larger than 1. So we know this has dimension 1. Okay, and that's the strategy for concluding. Okay, and I'm done here.